Okay, so in this video, I'm going to be showing you how you can calculate the derivatives of the inverse trig functions. I know when I was in Calculus 1 at least, we went over this topic really quickly and we were more or less told to memorize all of these. However, I think it can be a very useful skill to know how to derive them yourself in case you're terrible at memorizing things like I am, or if you just want to have this as a backup, if you want to double check your answers on tests, things like that. I think this is really useful to know how to do. Okay, so the very first thing we need to do is to find a general formula for calculating the derivative of any inverse function, and once we do that, we can then use it to find the derivatives of all the inverse trig functions. And in order to do this, we're going to start out with the definition of an inverse function that says if you compose a function with its inverse, then you'll just get back out whatever you put in. In this case, we put in x and we get back out x. Now, this is something you should have learned about in pre-calculus. However, if this looks completely foreign or you just want to brush up on inverse functions, I'll link some resources down below that will hopefully help you with that. But now, since we have this written out, we're going to use this to find the formula for a derivative of an inverse function. And the first thing we need to do is take the derivative of both sides, or the entire expression. And since this is a composition of functions, we need to use the chain rule. So we're going to get the derivative of the outside portion multiplied by the derivative of the inside, which is going to be the derivative of the inverse. And then we need to take the derivative of x on the other side, which is just 1. Now, we can just divide over this to the other side, and then we'll get that the inverse function derivative is equal to 1 over the function's derivative evaluated at its inverse. So I know that this may look a little confusing, but hopefully as we work through some examples, it will become more clear. But all this is saying is that the inverse function's derivative is equal to 1 over the derivative of the function evaluated at its inverse. So hopefully as we work through some examples, you'll see how to apply this formula that we just derived for the derivative of any inverse function. Okay, so first we're going to calculate the derivative of arcsine using this formula that we just derived. Now when you're first starting to use this formula, I think it can be really helpful to write a few things out before plugging everything in, so it can become really clear what you need to plug in, and it helps from making any small errors. Okay, so the first thing we're going to do is identify what our inverse function even is, because we're going to need to plug it in here. So our inverse function is going to be arcsine. And then looking at this formula, we see that we need the derivative of the function. But what is that function? Well, since our inverse function is arcsine, it makes sense that our function would be sine, and that the derivative of sine then is cosine x. And these are the things that we're going to need in order to plug into our formula. And I think at first it's just really helpful to write all this out. So now let's calculate. We're calculating the inverse function derivative, in this case, which is arcsine of x. Derivative is equal to 1 over the function's derivative, which we calculated right here, which is cosine x evaluated at its inverse, which is arcsine of x. Okay, so now all we need to do to find the derivative of arcsine is to evaluate this expression in the denominator, cosine of arcsine of x. Again, this is something you should have learned how to do in pre-calculus, but in this video I'm still going to try to explain to the best of my ability how you calculate something like this, because I know it can be really confusing and a lot of people do need a refresher on things like this. So I'm going to try to explain, but I'll still leave some resources down below in case my explanation isn't sufficient, or if you just need additional help with this topic. Okay, so I moved to the other side of my paper. So our goal is to evaluate what cosine of arcsine of x is. So first we need to figure out what arcsine of x really gives us in terms of information. And I think it's important to remember what inverse functions do. Inverse functions basically undo the actions of the function. And what I mean by that is, for some function f, if you input x and get out y, if you plug in y into the inverse function, you'll get back out x. So if you have some function that takes a value here, let's call that x, and turns it into y. So that's under the operations of f. Then the inverse function basically just undoes that, and it'll take y back into x. So hopefully that makes sense. Now, what does this specifically mean for arcsine, which is the inverse of sine? Remember that with sine, what you basically input into sine are angles, or values of theta, which are angles, and then you get back out a ratio of the side lengths, specifically the opposite side length over the hypotenuse. Now, since we're dealing with the inverse of sine, for arcsine, you put in this ratio of the side lengths, opposite over hypotenuse, and you get back out an angle. So basically what arcsine of x is telling us, this x that is inputted here, is putted a word? I don't know, is a ratio of the opposite over the hypotenuse side lengths, essentially. So based on arcsine of x, we can use that information to find the sides of a right triangle. So we have arcsine of x, and there's an implied over 1 here, so we can take opposite, which would be the x, over 1, which is the hypotenuse side length. Now, since we have two sides of this triangle, we can use the Pythagorean theorem, which says the hypotenuse squared is equal to both of the sides added together squared. So we can plug in these values. So the hypotenuse is 1 squared plus, or equal to, x squared plus b squared. So we'll solve for this side. We just need to subtract over x squared equals b squared, and then we'll get that b is equal to the square root of 1 minus x squared. Now we have all the information for each of the sides, and now it's really easy to see how we can solve for cosine, because again, cosine of an angle theta, which this is theta, is equal to the adjacent side over the hypotenuse. And we have all this information, so we can easily solve that cosine of theta is the adjacent side over the hypotenuse, which is just 1. So we'll just get the square root of 1 minus x squared. So cosine of arcsine of x is just equal to the square root of 1 minus x squared. So I'm hoping that this explanation makes sense. Again, I will leave some resources down below that will talk about this topic as well. So if you need additional help, you can look to those. I know that at first this can seem a little confusing, but I promise as you practice more and more, you'll be able to solve cosine of arcsine of x super easily and expressions like that really quickly. Okay, so let's move back over to our problem. We found that cosine of arcsine of x was the square root of 1 minus x squared, so then we can just plug that in. So the derivative of arcsine of x is equal to, okay, made a little mistake here, let's rewrite that. Arcsine of x, the derivative of arcsine of x is equal to 1 over the square root of 1 minus x squared. That's our final answer. Let's evaluate what the derivative of arc cosine is. So our inverse function is arc cosine of x. Our function then would be cosine of x, and the derivative of cosine of x is negative sine of x. So now we can plug this into our formula. We have the inverse function. Its derivative is equal to, in this case, arc cosine of x. Derivative is equal to 1 over negative sine, evaluated at the inverse function, which is arc cosine of x. So now we'll do the same thing. Our theta is arc cosine of x. this information here gives you the ratio of the sides. And in the case of cosine, it's the ratio of the adjacent side length over the hypotenuse. So we know there's an implied 1 here, so x over 1. And then again, our other side that we can find via Pythagorean theorem is going to be 1 minus x squared. So now we can just plug this in. Negative sine of arc cosine of x is going to be equal to negative sine, in this case, is opposite over hypotenuse, which is just going to be negative square root of 1 minus x squared, and we can just plug this back in. We'll get the arc cosine of x derivative is equal to negative 1 over 1 minus x squared. Okay, next example, let's find the derivative of arctangent. So our inverse function is arctangent, our function is tangent, and the derivative of tangent is secant squared x. Okay, so the derivative of the inverse function is equal to arctangent, which is 1 over the derivative of the function, which is going to be secant squared x evaluated at, and then all of that's going to be squared, and just remember that secant squared x is the same as secant x squared. Okay, so now let's evaluate for secant of arctangent. So our angle is arctangent. Let's draw our right triangle. Okay, so the tangent, remember, is opposite over adjacent. So our ratio of sides is going to be opposite over adjacent, and then we'll use Pythagorean theorem to solve for the hypotenuse, which if you do that, you'll find that it's x squared plus 1 or 1 plus x squared, doesn't matter. And if we know that secant of arctangent of x, secant is going to be hypotenuse over adjacent. It's the opposite of cosine, so hypotenuse over adjacent, we get x squared plus 1 over 1. Don't know why I wrote it that way. Okay, so we know that value. Let's just plug it into our formula now. So we have the derivative of arctangent of x is going to be equal to 1 over square root of x squared plus 1. Don't forget our original square here, which just gives us 1 over x squared plus 1. Okay, let's do one more example, and then you should be good to go to solve the other ones on your own. Again, I'm just writing out this formula. Especially when you're learning this, it's really good to just write it all out and avoid making small mistakes. Okay, so let's solve for, let's find the derivative of arc cosecant. So our inverse function is arc cosecant, our function is cosecant, and our derivative is negative cosecant arctangent x. Okay, so let's plug this in. So this is going to be 1 over the derivative of f evaluated at the inverse function. So for each of these x's, we need to plug in the inverse function. So we're going to get negative cosecant of arc cosecant of x multiplied by cotangent of arc cosecant of x. Okay, then we get 1 over, let's just bring the negative up, cosecant of arc cosecant of x is just x, and then we have cotangent of arc cosecant of x. Okay, so now we will solve for cotangent of arc cosecant of x. So our angle, again, is arc cosecant of x, and cosecant is, it's a horrible right triangle, and cosecant is hypotenuse over opposite. So we have our cosecant of x over 1, so we'll have x as the hypotenuse, and the opposite side is going to be 1. And then using Pythagorean theorem, again, we'll get x squared, square root of x squared minus 1 as our other side length. So now we need to solve for cotangent. Cotangent is adjacent over opposite. So let's just write that out. Cotangent of arc cosecant of x is x squared minus 1 over 1. So it's just x squared minus 1. So let's plug that in. Arc cosecant, oh my gosh. Arc cosecant of x derivative is equal to negative 1 over x square root of x squared minus 1. Okay. Hopefully you found this video helpful. If you have any questions at all, please write them down below. I would be happy to answer them. And yeah, I'll see you in my next video.